Okay, sorry for the late start. So I sent you yesterday the test, and here is what we had. Let's see if I can zoom this a little bit more. Okay. So the first one was a numerical question. So I wanted you to integrate this. And so you would have done a left-hand sum and a right-hand sum. Don't forget to multiply by 2 because that's the width of our rectangles. And we just do the left-hand sum, we get 530 feet. Right-hand sum is 330 feet. So our estimate is 430 feet. And then, which of the following statements can you justify from the data? And so we know that it's got between 330 and 530, and the skunk was 400 feet away. So it's not conclusive because 400 is within the error range. But because our estimate is 430 feet, there's a good chance the skunk might have been hit. Question 2. If this is 4, then the integral here is going to be -4 because these two areas look the same. -4, so that would mean that the total integral between -2 and 2 would be 0 by adding the 4 and subtracting the 4. The total shaded area would be 8, right? Because the area here is 4, the area here is 4. And then the average would be the 0 divided by 4 would give you 0. Here, the average value question. So you would have integrated this, you would have added up all the squares. You would have found that there were 8.5 squares there. Divided by the interval of 5, you would have gotten 1.7. If f is in pounds and x is in feet, then the integral f of x dx would have been pound feet or foot pounds. The one you wanted to put first, you would multiply it. In question 5, we see that B has the higher peak. A is quickest to peak, but the one with the greater biodiversity is B. So this was a right sum, and you would have gotten a lower estimate, an underestimate of that. N is 5, right, because there's 5 rectangles used, and delta T is 3. It's 15 divided by 5. And given what does this estimate give us? If you go ahead and count the squares, there's around 13.5 squares, or you can use the left-hand rule. You've got an answer of around 162, somewhere like that. What would be a more accurate answer would be around 180, 182, something like that. So if you've done a right-hand sum or try to estimate these white areas here, you can see that there is around 1.5, maybe a little over 1.5 squares extra that hadn't been counted. So that would have gotten you that estimate. What is the formula for the area between those two curves? Right, so that they're equal at 0 and 3, so that would give you your bounds of integration, and 3x is greater than x squared, so it would have been this integral right there. 8 was basically just another numerical integration. But since the curve is symmetric, the left-hand sum would give you the right-hand sum, and it would give you $15,000 if you do do that. And so then the total cost is 15,000 plus the 500 fixed costs. And finally, use 4 rectangles to approximate that integral. So since there's 4 rectangles, you do it every quarter. You have your function, and then you do left-hand sum and your right-hand sum, and you average it to get the estimate that one needs. And that's our test. Okay, any questions about that? Okay. So, what are we talking about today? Oh, yes. Okay, so hopefully everyone's got a kind of good idea of what an integral means. And so now we're going to go ahead and come up with doing some formulas for doing integrals and also for some other applications for using intervals. Okay, where am I in my notes? Okay. Okay, so we have an idea of a derivative. And so I want to return to that because we're kind of seeing that there's a relationship between a derivative and a definite integral, right? Because we had that fundamental theorem of calculus that told us that when we integrate a rate of change, then the total change is what the definite integral is, right? So there's some relationship between the integral and the derivative. So I want to define an antiderivative, and that's just going backwards with the derivative. So if a derivative of capital F is little f, that is, f prime of x equals little f of x, then we call big F an antiderivative of little f. So for example, we know that x cubed derivative is 3x squared. So 3x squared is the derivative of x cubed. Or another way of saying that is x cubed is an antiderivative of 3x squared. It's just reversing the order in which we say things. Right? And so I can replace that. So instead of x cubed, Elijah, give me a function. 2x to the fourth. Right, so the derivative of 2x to the fourth is 8x cubed. So that means 8x cubed is the derivative of 2x to the fourth. So that means 2x to the fourth is the antiderivative of 8x cubed. Okay, so you get the idea. So just using the word antiderivative just means you just swap the the function as a derivative, now you get the antiderivative and its function. Okay, it's just a way of thinking of it backwards. Okay, so let's first think a little bit about antiderivatives. Now, we know about the relationship between a function and its derivative when we do a graph. All right, so I've got to be careful here to say. So f is an antiderivative of little f. So that means f is the derivative, little f is the derivative of big F. Okay, so we know that if a function is increasing, then is positive. This is one of the first things we learned about when talking about derivatives. The relationship between a function and its derivative means that if a function is derivative, then it's, if a function is increasing, then its derivative is positive. If f is decreasing, big F is decreasing, and its derivative is less than 0. Okay, so what I've just done here is just translate this into terms of antiderivatives. Okay, if the derivative is positive, i.e., if a function is positive on that interval, then its antiderivative is increasing on that interval. It's exactly the same kind of relation. We're just putting things backwards. If a function is negative on an interval, then its antiderivative is decreasing on that interval. And if a function is 0 on an interval, then its antiderivative is constant on that interval. So this is exactly the same stuff that we said about functions and derivatives. We can say it in terms of functions and their antiderivatives. It's just basically like in English, it's just like swapping which is the object and which is the subject of the sentence. Whew. Talking too much. Okay. So let's do an example. Now we did lots of these kind of examples the other way around, right? When we talked about a function, we did a lot of things when we figured out what its derivative was. Now I'm giving you a function. I'm saying, well, the function is a derivative. So what does the antiderivative look like? Okay, so let's go ahead and do that. Okay, so here the derivative is positive. Remember, this is f prime is the derivative, right? So f prime is positive. So this means f is increasing. At 2, the derivative is 0. So that means at 2, it's flat. Here, f prime is negative, so that means f is decreasing. At 5, we've got that the function is flat. And here we've got that the derivative is positive, so that means f is increasing. Color short. Okay, so we're told that at f at 0, the function is 10. Okay, so it's increasing, so we're going in this direction, right? And we're going to go up to at 2, we're going to increase until we get to 2. At 2, it's going to be flat. Now, what is the value at 2? Well, remember, we've got that total change theorem, which says that the change in the function is going to equal the integral of the derivative. So between 0 and 2, the function f increases by 14, because that's the area. So at 2, we've got to be at 24. So we've got to join this line to this line. And we see that it starts off at its steepest and then becomes gentler and gentler until the slope is 0. So we start off steep until we get somewhere like this. Okay? Between 2 and 5, the derivative is negative, so that means it's decreasing. But we can figure out what f of 5 is, right? Because again, by that fundamental theorem of calculus, the total change is going to be negative 20, because the integral is negative 20. So at 5, we have to be at 4. We have to be flat at there, okay? And so what happens? We see that it starts off gentle. Here is where it's steepest, and then it eases off again. So we start off gentle, getting steeper. We go like that. And then finally, where are we at 6? Between 5 and 6, we know the total change is 12, so we add 12 to that. 12 plus 4 is 16, which is around here. Right, and we see it getting steeper and steeper because the rectangles are getting bigger and bigger as we get along. Well, that's what we get. Okay. So remember, when we started the class, the problem I would have given you is I would have given you this function and asked you to come up with this function. And that wouldn't be any problem. Now we're looking at it from the reverse view. I'm giving you this function, and I'm asking to give this function, right? Because how would we have done this before? We would have had the slope at different points. We would have figured out the slope, and we would have transferred them to this function, and we would have gotten something that looks like that. Whew. Okay, that's a big thing for today. Okay, that's the thing that you've got to wrap your mind around and that you've got to understand. If you understand that, then you're going great. Okay. So the question, let's go back. We sketched the function. Give the coordinates of the local max and min. Okay, the local max and min occur at the critical points where the derivative is 0. That means we want to make sure we put in these points here. Because we were given the initial value, we can come up with this curve, right? We know that we started at 10. Because we could have started anywhere, right? And we would have gotten just a parallel curve. Again, because the derivative tells us how fast we're going. So we've got to know where we started from to know where we are at any particular point. Using the area, we can only figure out the change. We need some point to start off as a base. So how does concavity come into this? Okay, so remember we had a function f. We had f prime was its slope, and f double prime is its concavity. Now we're switching emphasis. And so this was the function slope. Now got here is a function. Let me call it g, because I call it f and g. You don't know the difference between a big F and a little f, so I do that, right? Then we've got the antiderivative. And then we've got its slope. And we're just changing the emphasis of how we're looking at functions. At the beginning of class, we looked at a function, and then we looked at its slope and then its second derivative, which was its concavity. Now we're looking at functions here. And so we go back to the antiderivative. And if we take the derivative of this function, we get the slope of g. But if g equals f prime, then g prime equals f double prime. So the slope of this function gives us the concavity of this function. It's just that kind of relationship. Okay, so this thing here equals this function here. So the slope of this function is the same as the concavity of this function. Right. So if we've got an antiderivative of some function, right, capital F is the antiderivative of little f, then if this value slope here is positive, that means this function, second derivative, is positive. And we know that if a second derivative is positive, then we've got something which is concave up. And if this slope is negative, i.e. g is decreasing, then this function is decreasing. F double prime, this function here, its concavity is negative, so it's concave down in that interval. So it's really easy to get mixed up, right? Because you've got two functions, and we're just looking at the relationship between the two functions. So when we talk about an inflection point for this guy, right, that happens when f double prime equals 0. But if f double prime equals 0, g prime equals 0. So that corresponds to critical points. And so when we go back here, okay, so the critical points of this thing here occur here and here. They should correspond to inflection points of the curve before. Let's just check that. Oops. What am I doing? Oh, here we go. And they do indeed, right? So, anyway, let's answer some questions. See how we go with that. So here is a function here. Which one of these guys can be the antiderivative of this function? Or put another way, so we want this to be an antiderivative of this. We want this to be a derivative of one of those guys over there. Would be D. C, right? Okay, because let's have a look at this function. Let's just have a look at it. What is this antiderivative doing? So it's going to start at some point. It's going to be increasing, right, as we go along here because the area is positive, right? It's going to be increasing A until we get to 3, and then it's going to be flat, and then the function is going to be decreasing. And if we look at this, there's only one candidate that does this, right? This guy increases, is flat at 3, and then decreases. This guy, right? We want something which would be positive all the time. This one, we would want, yeah. So none of the others kind of work. Because this is always decreasing, so this would be have to be negative, and then this would be positive, negative, positive. So this is the only one that works. What about this guy then? Okay, so here is a function. Which one of these can be the antiderivative of this? Or you can think in terms of derivatives, okay? So this function here is positive, so that means what are we looking for? An increasing function. So we go look, and we see straight away that there's only one function that's increasing. This has to be it. And let's just check some more things. It's 0 here and here. So we need our function to be flat here and here. That fits. Here is where it's steepest. That will be an inflection point. You see an inflection point here. So we can see that C works as well. Okay, what about this guy here? So everyone just spend half a minute just thinking about, I'll give you half a minute to think about it. Okay. Someone give me an answer. A works, right? So what are we looking for? We're looking for a function which is decreasing, right? Because this is negative. It's flat at 0. and then it's increasing. It does. So this is the sneaky thing about antiderivatives. So you notice that I talked about the derivative and an antiderivative, because the derivative of x squared is 2x, right? So so x squared is an antiderivative of 2x. But what's another antiderivative? What's another function that we can differentiate to get 2x? What's the derivative of x squared plus 1? It's 2x, right? Because we can always add a constant, and when we differentiate, that constant's going to go away. Okay? So we can always add a constant to our antiderivative. And what's the difference between f of x and f of x plus a constant? They're just parallel, right? You just lift it up by c, or if c is negative, you push it down by c. So this has two answers, A and D. So there's only one ever derivative, right? Because the derivative gives you the slope. There's lots and lots of antiderivatives, right? Because we're looking at total change. So based upon where you start off, you can start off anywhere, and your antiderivative will then just be parallel to this one here. So, you know, there's another. So for every number on the axis here, there is an antiderivative which goes through it, and you just get a whole family of curves parallel to one another. So that's what makes a little bit of difficulty in this thing, because there's that little bit of ambiguity on plus C. Okay, time for a numerical question. So here, we've got the derivative. Which one of these could be the antiderivative? Which one of these is really f of x? Which one of these is really the antiderivative of this curve? Okay, so the derivative gives us the rate of change, right? So it's telling us that how much is it increasing over this interval? 1. 1. Well, how much? So between 0 and 2, it's going to go up by 2. What's it going to go up by between 2 and 4? No, I mean, what's, it's a triangle. What's the area of this triangle? 1. Okay, what's the area of this triangle? 1, but it's below the x-axis, so it's -1. So we're looking for a change of 2, 1, -1. And with that information, go back and tell me which functions work. Sorry, the trick you like that. Yes, all the functions work. So again, this is a terrible test question, but it just hammering home the point about parallel functions have the same derivative, so they're all possible antiderivatives. Right, because if we start at 1, we go up by 2, up by 1, down by 1. That's exactly the slope derivative here, right? Up 2, up 1, down 1. Up 2, up 1, down 1. Up 2, up 1, down 1. Okay. Graphs of the derivatives of 4 functions. So these are the derivatives of 4 possible functions. For the functions, not the derivative, right? So these are the graphs of the derivatives. I'm asking a question about the function that the derivatives are, about the antiderivatives, right? This in increasing order, which has the greatest change in value on the intervals shown. How do we answer this question? How do we get change in the function from the graph of the derivative? We take the interval, so we look at the area under the curve. So another way it is saying arrange in increasing order the area under the curve of these functions. Okay, so that's a question that you can kind of answer. What's the area under this graph? 8, right? 4 by 4, it's a triangle 8. What's the area under this rectangle? 8. Here we've got 2 rectangles. The area under this one is 6. The area under this one is 2. So the area here is 8. Oh, how do we do this guy? Okay, so we've got a square here. It's 4. We could add this triangle to this triangle to get a square of 4. So we can see the area is 8. Or we can see this is a trapezium. This is 4. This is 2. This is 2. Again, the area is 8. Just like before, everything's the same. Again, that shouldn't surprise you. If change is given by area, there's lots of ways in which you can get the same area underneath the curve between 2 points. Okay, same question. Okay. So these 2 guys have definitely got different areas. So it's not any this time. Can someone give me the area for number 1? Let's have a look. So we've got this square, the rectangle here, which is 2 by 4, is 8. And then we've got a triangle 2 by 2.
Oh, I did find 4. Okay.
Right, so I think it's 8 plus 2, I think. Was it 2 by 2, or half of it is 2 there? It's 10. Anyone come up with the area for number 2? 12. There's lots of ways you can do that. You can get this rectangle here, plus these 2 triangles here, and you get 12. What about 3? Can everyone see that 3 is the same as 1? right? Because we've just reflected it. And so it's the same area underneath. It's underneath the curves. What about 4? Can anyone see that? Anyone see that it's actually the same as this, right? Because we've just swapped these two pieces. So the area underneath the graphs is exactly the same. Yep. So it is D, is the answer. Oops. Can we read this question? Assume here we've got some antiderivative and that f of 0 is 10. So f of 0 is 10. What does capital F of 5 equal to? Everyone, don't say anything, just think about it for a moment. We've got to figure out the change in the function from 0 to 5. This is the derivative of this function. So how do we get the total change from the derivative? We integrate, right?
That's the graph of the derivative.
That's the graph of the derivative, yes.
So doesn't it just say f of x, not f of x?
It's just little f of x is the derivative of big F of x, and we want to find big F. So big F starts at 10. Right, when it gets to 3, it's at 17, because we've added 7 to it. But then from 3 to 5, we subtract 6 from it. So the answer is E, 11. Right. Last one. Okay. So it says here, where is there a local maximum on f of x? So again, this is the graph of the derivative. So when will we see a local maximum for the function itself? Right, it's going to be where the derivative is 0. And how can we tell it's a maximum? It goes up and then goes down. So we want it to cross the axis. Beforehand, we want it to be positive, and afterwards, we want it to be negative. So what would that be? If this is the derivative, then the function has a maximum here, right? Because it's going up and then it's going down. Again, if we think of it in terms of area being the total change, that makes it simpler, right? Because here we see the area increasing and then decreasing. Here we see the area decreasing, then increasing. So this is a minimum. So the answer to this was C. Here is a local max. There is a local min. Okay. So that's today's class. So we introduced this idea of antiderivative, so I want you to kind of mull over this a little bit. Because it's going to be what we're going to use to be able to figure out how to get a formula for integration. Pros class. See you guys. You too.